as far as this lecture is concerned, this presentation is concerned, it's not that I'll be going very deep into any one topic, but this is meant to give you an overall view about what would mean by sustainable groundwater, sustainability of groundwater systems, and and before that, I would like to give you a complete view of what I'm going to present to you. Let's read them. Okay, it's important that you keep in mind what all the important things I'm going to present in this 1 hour. I would briefly tell you about the groundwater system, and then the difficulties in conceptualization of this, and then we'll go into the modeling aspects of it and the modeling tools. This particularly because we are engineers, finally we work with models of anything so that we can create scenarios and get the results out. And then very important for understanding sustainability is what is recharge and what are the methods of recharging. And particularly, if you look at the fourth point, artificial way of recharging the system, groundwater system. Then we, after having understood what we mean by groundwater systems and a few things about the groundwater issues and things related to groundwater modeling, we come to the sustainability aspects of groundwater systems. Okay, and that's the fifth point that you see on the screen now. And now later we look into the importance of groundwater resources from the country point of view, and then from Karnataka state point of view. Dr. Rekha informed me that we have participants from all over the country, but I, coming from Karnataka, from Mysore city, I thought I'll touch a little about the resources in Karnataka. This shows where we stand as far as our resources are concerned, groundwater resources are concerned, and then the importance of getting into sustainability aspects of groundwater systems in our place and also in other places. Okay, unless we know the problem, the gravity of the issue, we will not be able to provide. We will not be serious enough to provide solutions. So, from that point of view, if you were to look at point number 6, we look into what's the status of groundwater systems in India and Karnataka very briefly. Then we look into what happens when we pump. Okay, now I'll touch this in detail, but then at this point of view, why is this important? Why do we look at the issue of pumping? Because in 1970s, around 70s, that's when they started putting up bore wells. They started installing bore wells. Earlier, the technology was very expensive, was almost non-existent, and 80s you had the technology around, and then for reasons you all know, 90s, you had the technology and also you had the finance, a lot of money with the farmers at least. When I say talk about money, some free money with the farmers where they started thinking about putting up bore wells. So you had the technology and you had the finance. And so they started putting up the bore wells to pull up water from the groundwater system. And this really affects. And so that's the reason, 7th point, we look into effects of pumping. Then we again come back and look at what's the status of the groundwater systems in the whole of the country in a different way, okay, which you'll understand when you start the presentation, when I come to that particular slide. Now, what I'll be talking about today will be from quantity point of view. And I talk very less of quality. So it's not that groundwater systems are not they don't suffer from quality issues and pollution issues, but then in the country, at present we are grappling with flow modeling, and then pollution modeling sits on flow modeling. So when we have not done a good job flow modeling, pollution modeling, and then talking about pollution would take a secondary about quantity issues and then sustainability issues connected with quantity, and we go on. Okay, so we talk very less of vulnerability, rather quality point, and so we touch the quality of groundwater systems and sustainability issues in only one slide today. Okay, and then we come to the regulations of groundwater. Okay. Now, before that, uh, how do you implement whatever we have learned? It has to be through a structure, what we call as integrated water resource management, where there are many players. The government is one of the players, the private sector is a player. And so we give a realistic picture to this. Okay, how do you get into all this? How do you maintain the sustainability of groundwater systems? And then all this is possible through a law. Okay, so luckily in India, we have a law, and that's known as the Groundwater Act. And so we look into it. And finally, there's one very interesting issue due to which most of the states in South India are suffering, that is vanishing of the tanks, and what was the impact that they had on the groundwater system. Okay, so these are some of the things that I want to sensitize you about in my presentation. Okay, so let's get into it. Now, please keep in mind that my presentation doesn't involve deep mathematics at all. Rather, no mathematics involved here, and much of it is explanation, and maybe we'll be followed up with some deliberations with you in the feedback. In the question and answer session. Okay, so let's get into the first slide now. This was I understand that most of you are faculty, and so you have a what you call feel for hydrology, and also for a relatively good feel for groundwater systems. But for formality, I thought I'll explain in brief. And so what you see here, is the part of the system. Okay, so you have the rainfall, and then the rainfall infiltrates to the soil, and then it percolates to the soil and then reaches the groundwater table. Okay, right? And so please also remember that whatever rains doesn't reach finally the water table, right? In the process of percolation, much of it gets what you call pulled up by the plants and trees as evapotranspiration. So there are episodes in which the groundwater is recharged. Okay, so finally the rainwater that reaches the groundwater table or the groundwater system here is known as recharge, and most often it reaches the groundwater system. The recharge reaches the groundwater system in episodes. You may have about 6-7 major episodes in a year where you have the replenishing of the groundwater system. And then finally, the water that is entering, as recharge the groundwater system, finally, where does it go? It goes to the nearest stream. And the groundwater system is quite deep. It goes to a stream a little far off, okay? And that is what you see here, right? And so the upper picture that you see where my pointer is running around is when in monsoon, you have all the water moving towards the valley, and then the whole of the valley is flooded with groundwater, okay? And now the lower figure is when in summer times when we don't have rain. And so in a way, the river itself is feeding the groundwater system. All this shows that the surface water is intimately interacting with the groundwater system. Okay, so let's go to the next slide now. And I don't intend to give you a complete picture. This is not the place to do it. It requires hours together to give a complete picture about the groundwater system and the surface water and groundwater interaction. But then I wanted to sensitize you about the gravity of conceptualizing or the difficulty of conceptualizing the groundwater system, and then the modeling that goes after that. Okay, now for your knowledge, what I want to bring to your knowledge is that the whole of South India, let me talk about South India because that's what I'm more exposed to, is hard rock aquifers. We have hard rock aquifers here. We have granitic gneiss, and it's something like this. At the top, you have the soil, and then you have something known as a regolith, and then it's followed with the saprolite. Okay. So it's all weathered rock, and the soil at the top is hardly about 1 or 2 meters. And you see that at the side here. Look at the scales. Don't take it for any a proper scale. This is an exaggerated vertical scale here. You see that you have the saprolite for about 15 meters, and below that you have fractured rock. Okay, right? And so this roughly around 15 plus about 20, 35 meters is the groundwater system that you're talking about. This is where most of us are making mistakes. Okay, it's a complex system that, and so you cannot follow whatever you have learned as far as sandy aquifers are concerned. Okay, but particularly in South India, if you want to go for modeling, you have to be aware of this intricate details, and this is hydrogeology I'm talking about. And it's about 35, 50 meters of system thickness that you're talking about. And then you have fractures, and below that you have solid rock. Okay. Why am I showing you this is to bring to your notice that conceptualization of the groundwater system is complex. As it is, you have interaction of the groundwater system with the surface water system. At the same time, inside the system, groundwater system, the system is not that easy. You have this complexity in it. Okay. Now, let me go to the next one. Next slide. This is another detailed shot, and it shows a picture of a bore well where these layers are very much visible. Okay, so you see this. One second. So from here to here, I mean, I'm gonna write it here. This is your. I'm using a what you call highlighter here. This is your soil. It's hardly about one and a half meters, and then from that point onwards, one second. Yeah, from here to here, you have that saprolite that we're talking about. Okay, right? So this is the saprolite that we're talking about, and then after that you have the regolith, and then at about 50 meters you have your base rock. Fine. Now, what is involved as far as your conceptualization of this groundwater system is concerned is a type of of the layers. Okay, when you're talking about the layers, it much has to do with the layers. Okay, in the conceptualization of the groundwater system and also later modeling. So you need to think about the soil layer and the regolith layer and saprolite and the thicknesses and the bounding surfaces. Okay, the levels, the topographical features about them, and then two things are important as far as the groundwater system is concerned. Okay, it is the storage of water, and the parameter specifically takes care of that, and it is movement of water in the system, and then the hydraulic conductivity parameter, the parameter hydraulic conductivity takes care of this. Okay, so this is just to show you how much is involved when we talk about groundwater systems. Okay, now this is a screen which I picked up from one of my PhD students. She's working on the western the groundwater systems, the Western Ghats. Okay, so we are trying our best to what you call conceptualize the system, and this is how we conceptualize it. Layer one is about you see here. Layer one is one second. So you have that here. I'm here. I'm reading here. Fine. So layer one is 0.6, about 0 to 6 meters. 6 to 12 meters is layer two, and so on. Okay, we go up to about 30-40 meters here, and then each layer would be having its own specific yield parameter value, and then the hydraulic conductivity parameter value to it. Okay, now all this conceptualization goes into your modeling, and what do we have here? Now, the system, modeling, you can represent the system as a lump model. You see the tank here, and then you have the inflow to it, and the inflow can also be laterally deeper in the aquifer from the adjacent aquifer. You can have inflow to my aquifer, and so and then outflow is to the river. Okay, and what we call it as base flow. It goes to the nearest stream or to the river, and we give a special name to it. We call it the base flow, and then we have nowadays, since about 1980s, 90s, a lot of pumping. So you have one more outflow now. In a natural system, we had only recharge and as the inflow, and then this natural outflows, but the pumping is a new artificial, what you call, a component of the balance we have. Okay, so what you see to the right is the balance. So input minus output is equal to storage change. But the system is quite complex, and so there is spatio-temporal variability, okay, in everything. The topography is changing, and then the land cover is changing, and then and due to the land and the soils are changing, the layers, the types of layer, the thicknesses are changing, and so you have it as a lamp system, you had to think the system to be varying both a solution to this partial equation. So what we do is we use finite difference scheme to convert into and this equation, we apply it throughout the domain of the groundwater model, okay, right? And this has been shown here. And if anyone's interested, much more interested than what is being shown on the screen, you can get back to me after this. I can give you good literature for this, okay? Now, for the time being, I'm just telling you in very brief way what modeling really is, okay? So it's about the partial differential equation, and then there's no solution to a partial differential equation, so we use finite differences to what you call get a solution. We linearize it, and then we apply it, having made a grid onto the groundwater modeling domain, okay, on my domain, right? So this is how it is, okay? So the grid, is put on the domain of my groundwater modeling. This is what you see here. So this is what you see. This is the domain of my modeling, and so below that you have the layers. Okay, so how many layers you have, that depends upon your your area. Fine, and now so we have something known as a grid cell, and then the grid cell is connected to the neighboring grid cells, and so we have a general equation the way it is shown here at the bottom. Okay, this is incidentally from a what you call computational tool that we use known as ModFlow, and then as you see here, the domain may have how many grid cells. If it's the grid size depends upon the grid size. So maybe if it's about 100 into 100 grid size, you have 10,000 grid cells. So for each grid cell, you have a linearized equation. So you have 10,000 linear equations to be solved simultaneously. Obviously, you cannot do this in a calculator, and hence what we have is we have software tools for that. And that is what I call as modeling tools, okay? And now the most popular one is popular tools are this, okay? I'm talking about groundwater modeling now. I have not touched surface water modeling. Why is surface water modeling important? Because the recharge is developed through a surface water model, and then that recharge is given to the groundwater model. So due to lack of time, I have not touched surface water modeling and surface water modeling tools here. Now, I just started off with groundwater modeling tools, and you see that we have something known as model muse, and then processing mod flow. And incidentally, these tools that I'm showing on the screen, they're freeware. Okay, now we believe in freeware nowadays. Okay, people don't rely unless it's a very involved, what you call consultancy work. You usually don't where presentations are very important, and unless we have such a situation, we go for freeware, which all these freewares, they do as serious a business as commercially available softwares. Okay, incidentally, groundwater. The groundwater modeling system, GMS, is a commercial where it's quite expensive. Okay, it's about 3-4 lakhs for an academic version. uh, but then whatever groundwater modeling that you want to do, you can do with the freely available what do you call software on the web. Okay, so Model Muse and processing ModFlow, right? And then uh, I have been talking to you about groundwater system not being independent of the surface water system. So what has happened over time is that people have coupled surface water modeling tools with the groundwater modeling tools. Okay, so we have coupled groundwater and surface water models, and GS Flow is one such a software suite or software tool that's available. And again, this is freeware from USGS. Okay, and if someone's interested, I can you can search on the web, or if it's difficult, you can always get back to me. I'll give you the links. So now after that, I'm going from one level to another. I'm third level now. Okay. So in this water management and planning tool, this incidentally integrates this tool. This integrates both the surface water model and the groundwater model in a GIS atmosphere, and also gives you management tools, okay, and planning tools in it. And incidentally, in this software, they call it as a module. And I'm talking about FreeWAT now. So the first level, let's go back. Let's go back and then start off once more now. First level, groundwater system. So you do a good job of groundwater modeling, and then you couple your groundwater model to surface water model through GS Flow. Okay, again, which is a freeware. And then you cannot stop here, because your results have to be used by the end user, and that's the wider society. Okay, particularly the farmers. And if that has to happen, you have to bring in planning and management, integrated watershed management, and planning has to be looked into. And so you go to the next level of your software tools, and that's this one, what I just showed you. And now, if you were to recall, let me go back to this. You see here in this screen that the system, one of the important inputs to a system is recharge. Okay, and okay, and another component is the pumping. So let's look into the recharge aspect. Fine, and let me go back to the slide that we were into. This was the slide. Okay, I'm sorry, I had to go back to the earlier slide. So let's talk about this aquifer recharge. You see the figure to the right. So it rains, and then not all the rain finally goes to the groundwater system. And whatever part of the rain that goes to groundwater system is known as recharge. Okay, now this is what we want to estimate. You want to do any what you call calculations, you had to know how much is the recharge that's going to the groundwater system. Sustainability has to do with this component. Okay, if you can find out recharge, then you can think about how much of water that you can pump out. How much of water that you can pump out. Okay, in a very crude way, we can say however much is the recharge is the extent to which you can pump out water. This is what comes to mind, but this is not totally true, but partly true. We'll look into the details a little later. Okay. Now let's look into recharge, and I have put up a few things here. Okay. So the recharge varies spatially and temporally. Okay. Right. It's not the same in the catchment, in the catchment that you're talking about, or the watershed that you're talking about, and it depends on factors like land cover, soil, and then geomorphology and geologic characteristics. Fine. And now you need to calculate it at over a long time, over 10 years, 15 years is the time span over which you need to calculate recharge. These are some of the things that are connected to estimating recharge in your groundwater system and aquifer, or in your watershed. Okay. And then people, what you call, mix up infiltration with recharge. Infiltration is the water moving from the surface into the soil. Okay, that process known as infiltration. And whatever water infiltrates doesn't finally move to the groundwater system. The infiltrated water, it is in the soil and starts moving down. And by the time it moves to the water table, groundwater table, much of it is evapotranspirated. So only a small part of the infiltrated water goes into the groundwater recharge. Okay, so that this was put up. This point that you see was put up just to make you aware of the difference between infiltration and recharge. Okay, right. And now we have diffuse recharge and concentrated recharge. Okay, what is diffuse recharge? The recharge that occurs to the soil is known as diffuse recharge, and the recharge that occurs or reaches the groundwater system through lakes and rivers and other water bodies is concentrated recharge. Okay, and even water escaping from your sewer pipes, you can maybe you can club it in diffuse recharge if you were to be in an urban area. Okay, so now because it's a very important component of your water balance, we have methods by which we can estimate recharge. So I bring to your notice a few important methods. So as you see, you know, there are methods based on unsaturated zone, that is the soil zone. And there you have things like lysimeter and chloride balance method. Okay. Now, what you see in the figure is a lysimeter. Okay, this is a lysimeter here, right? And this is what you call embedded into the ground. Okay, so you see only the top of the lysimeter. You see the man standing here, that should tell you the scale. Okay, so the lysimeter, as you see in the figure, is about 250 what you call centimeters deep, and roughly the height of a man, or about 1.5 times the height of man, is the length of the lysimeter, and the diameter could be about maybe 2 to 3 meters. Okay, and now as the water passes through it, you know, finally how much of it reaches the bottom of the tank gives you an idea about how much is the recharge. Okay, there are also complex methods like chloride balance method, which I don't want to get into. I just wanted to sensitize you that this component, you know, the recharge component of the groundwater balance, we have means of estimating it. Okay, and you'll also understand why I'm particular about telling you about aquifer recharge. There's something known as groundwater estimation committee report, and where they teach you how to estimate recharge, and this is based on a similar method. Okay, let's go ahead now. And right, and when you have recharge passing through your soil, you know, you can also model it, and that's known as water zone modeling. And then we also have software tools to take care of that. And one very popular software is Hydras. Okay, right. So the other important method is a method based on the groundwater data, particularly groundwater fluctuations. Okay, so you see here a hydrograph. Okay, you see here a what is a hydrograph? The groundwater levels, you know, when you observe it for a long time, and when you plot, you know, you have a hydrograph. And from the hydrograph, you can you have the water level rising during monsoon time. And if you were to find the extent to which the water level rises and multiply it with the specific yield, you'll know how much of water has recharged the system. Okay, the groundwater system, right? And now other popular ways of doing it is using your stream flow information. Okay, you have the stream flow hydrograph, you go for base flow separation, and you find out the quantity of water in the separated base flow hydrograph, and from that you can know, and you do it over maybe 10 years and then get the average, and from this you will get an idea about how much of water has recharged, because whatever recharge in a natural system should finally come out as a base flow to the nearest stream. Okay, so this was not to teach you in depth the way we estimate recharge, but to sensitize you that there are ways by which we can establish ways by which we can estimate recharge through groundwater system. Okay, right? Over time, you will understand this importance. I'm insisting that you what you call mark the term recharge. Okay, groundwater recharge. Okay, and now again you have a lot of software tools for base flow separation. Okay, and again USGS has a nice suite of software tools which are freely available, and you can work with them. Fine. Now This is on I was talking to you about the Central Groundwater Board, and then we have something known as the Groundwater Resource Estimation Committee, okay, which gives us how do I put up as a manual by which we can estimate the recharge. And basically it is nothing but the groundwater balance equation. And what is important is you have different components here. Okay, for example, this RSTR stands for recharge from steam channels and so on. So you have evapotranspiration, so on, so on. And then very important thing here is you see the red box here, this part, okay, which my pointer is showing to you. There you have delta H is nothing but the groundwater level fluctuation for that year into specific yield into area, okay. So this is a major input to this equation. And by chance, if you don't have the other components, and if you were to find the other components to be insignificant, your recharge could be just this, okay. So you can drop all this from this side. So I'll just maybe from this side, you can drop all these components, and then your groundwater recharge can be just this part now, okay, right? So this part, right? And so this is the basic basis for how to calculate groundwater recharge using the groundwater estimation report, okay? Now, this shows you the different components. You were talking about these components, right? All these components. So roughly these components are shown here, okay, right? So the water level fluctuation is this, okay? This could be your earlier water level, and due to recharge, it goes to this level. So this is your delta H now. This is your delta H. I hope you can see the screen. This is your delta H, right? So as I was trying to tell you earlier also, there are two important parameters that we work with in groundwater system modeling, and that is specific yield. This has to do with storage, and we deal with conductivity, K. This has to be do with movement of water, transmission of water, movement of water, okay, movement of water. Okay, now, let's go to the next one now. And the recharge can also be calculated by the method that I just showed you, and also by groundwater modeling, okay. Like one of my students was working with a model known as IA checkers. It's a simple model, a lump model by which we can not only model the surface water system, but can also get the groundwater component. Okay, you see this line here. This is the base flow. So once you separated the base flow, and in this hydrograph, the area under the base flow would give me the volume, okay, the volume of base flow, and then the volume divided by the number of years gives me how much is the recharge, okay, right? So this is another way of doing it. So there are different ways of finding out the recharge through groundwater system. Done. So let me go to the next part of my presentation now. And whatever we are talking about till now was natural recharge. Now, the natural recharge can be augmented, can be enhanced by artificial recharge, okay? Artificial recharge. And these are the different ways by which you can artificially, recharge the system. And these are the popular methods by which you do it. And there is one very nice, manual by Central Groundwater Board, which I can share with you a little later. Due to lack of time, I did not bring those references in my PPT, okay. I'll share the references separately after this presentation, or maybe by tomorrow, okay. So this is a list of ways by which you can do artificial recharge and augment the natural recharge, okay. You are increasing the recharge system. As it is, there is a natural system, and to the natural system, you're adding more of, to the natural recharge, you're adding more of recharge artificially, and this is the way to do it, okay. You can do it by flooding and by ditches and furrows and recharge basins and bench terracing and then contour bunds. and then gully plugs. I have a few pictures for you to understand this. Okay, so let's go uh, uh, to the details now. So why do you want to have artificial recharge? To increase recharge beyond the natural one. Okay, so water supply is maintained for once you have augmented recharge or what you call also as managed aquifer recharge, you can have a water supply for your needs, meeting your needs for a longer period, because the groundwater storage is a huge storage that exists below your feet, and and hence you can always what you call exploit it and make use of the water for a longer period during non-monsoon times also. Okay, so I hope you understand these connections now. Uh, if you want to go for more of recharge beyond the natural one, then you need to be adopting these techniques. Okay, the techniques that are given at the bottom, right? So let's go to the next one now. And this is what I was trying to tell you about artificial recharge. Okay, so you have something known as gully plugs here. You see that here. So these are the gully plugs. So you have a very small stream. You build a small what you call a check dam there, and so and incidentally the name that is given here in our places is we call it the gully plug. Okay, and then we have percolation tanks. You build a lot of tanks so that water in monsoon times you fill up these tanks, and so and the water would have been lost. The surface water would have been lost. Okay, the runoff would have been lost, and you avoid the loss by building this tank. So water gets stored here, and slowly water percolates down to the groundwater table. It recharges the groundwater system. So you call it as a percolation tank or recharge basin. Okay, so these are your contour trenches. So you see the trenches. I hope my pictures visible to you nicely. You see the trenches there. Okay, right? So maybe I'll draw one of the trenches for you, right? This is a trench. You have another trench now. Why do you have the trenches? When it rains, water can, the rapid movement of water is what you call controlled. And so water gets filled up in these trenches, and then water percolates deeper into the ground and reaches the groundwater table, okay, right? And now you have check dams, okay, right? You see that this is a check dam. I hope you see this. This is a small check dam, and incidentally, it has been constructed in a plantation of a farmer. And you have a gully plug here. This is a gully plug here. This is the gully plug, and check dam. So water goes and stops here. Water goes and stops here, and then you have percolation of water. The water finally infiltrates the ground continuously, and then passes through the soil, reaches the groundwater table. Okay, so all this is what we call as artificial recharge, artificial recharge, or a fancy name to this is managed aquifer recharge. Okay, managed aquifer recharge. It's here. Okay, so let's go ahead now. Now, finally, after having understood to some extent what the groundwater system is and how do we model it and all that, we look into the sustainability of groundwater resources. Okay, we start getting into the sustainability aspects now. By definition, let me take the liberty of reading it for you. Sustainability is development and use of groundwater in a manner that can be maintained for an indefinite time without causing, this is important, without causing unacceptable environmental, economic, and social consequences. Okay, so now let me put it like this. Okay, so you have your groundwater system, and you have your recharge. Okay, you have your recharge, and this is your storage, and then you have your base flow coming out. This is your base flow. This is your base flow. Done. And now, this is the natural recharge. Okay? This is a natural recharge now. And now what happens is how the recharge is over a long time equal to base flow, right? And now this fluctuates, no doubt. During the monsoon times, the groundwater level goes up, and during non-monsoon time, the groundwater level falls, and the fluctuation is about 2 to 3 meters. Okay, 2 to 3 meters. But the tank never gets emptied. Okay, the levels fluctuate, but the tank doesn't empty. Okay, but then when you start pumping out water, this is your pumping. What will happen now? The tank gets emptied. Tank gets emptied. Okay, now this base flow that you see, roughly it is a function of the head here. this is the head that you're talking about, head of water. So it's a function of head now. As the system empties, the head that drives the base flow becomes smaller, and so base flow becomes smaller and smaller. Okay, base flow becomes smaller and smaller as the system empties. And now much of it has to do with your base flow. Okay, the base flow finally gets into the stream, and all the riparian, what you call areas get affected now. The local plants and trees that were depending upon the stream flow, and this stream base flow, you're talking about the base flow that is occurring through most of the year. And if the base flow were to totally disappear, the streams start running dry. You have stream flow only during monsoon times, and non-monsoon times the stream is dry. And what can happen is the vegetation can get affected. Not just the vegetation, a lot of people downstream are also dependent on this small stream flow during non-monsoon times for their water supply. And so you don't have water supply to most of the villages downstream now, right? And so what should you be doing? You should see that your recharge, you balance it between your pumping plus your base flow, right? Done. And now look at this equation. Now this equation is important for me. This equation, recharge is equal to, you have to balance between recharge, your pumping and base flow. Now the problem with us is your pumping is too very high. What should you be doing now? Then you have to augment this left-hand side with your artificial recharge. So RA now, let's call it as artificial recharge. That should be equal to pumping now. So pumping can go up, and so still you can maintain some certain degree of base flow. Okay, certain degree of base flow. Let me delete this. Okay, this also. So this is something very important. So the whole of sustainability has to do with this. And 1 second. So this base flow. So now you maintain a base flow. If you want to increase your pumping, look at the second equation. What should you be doing? The left-hand side should also be increased. And natural recharge, it keeps occurring. Okay, only thing that can happen with a natural recharge is it can get reduced a little or get enhanced a little, but you cannot do much with your natural recharge. So what should you be looking into? Artificial recharge tools and what you call techniques by which you can go for artificial recharge had to be looked into. And hence now what you can do is you can pump out more water. At the same time, maintain base flow. This is common sense. Okay, the whole of sustainability has to be that in a technical way, right? So let's read it. And so what do we have? Sustainability is development and use of groundwater in a manner that can be maintained for indefinite time without causing unacceptable environmental, economic, and social consequences. Now, maybe as we go ahead, I'll also bring it to notice what happens when the groundwater table falls. When the groundwater table falls, the pumping has to be done from deeper depths, and due to this, you had to go for bigger pumps and more of electricity. It becomes expensive. That's where the economy is affected. Okay, when you don't maintain the sustainability of the system, the groundwater system, economy is also affected. And now the water table drops to such an extent that the system empties, or the groundwater table is so very deep that it's very, very, very expensive to pull up the water, pump out the water. Okay, and now all the social consequences follow. Before I forget, let me give you this. How do I call it, as a real life anecdote. Okay, when I was doing my PhD work, I used to visit a place known as Tarkanambi, where the fields are rain-fed, and since about 20 years, they have put up a lot of bore wells. Now, what has happened is I was speaking to one of the farmers there, and the farmers usually have about 2 to 3 acres very typically. And this farmer uses, and I see 3 or 4 bore wells so at some distances in his 2-3 acres. Okay, and ask him, what is this that you have 3 bore wells? He says, sir, the first bore well is dry, and it was not very deep. Okay, and then I was advised to go for the second bore well. I put a bore well and also went a little deeper, and after pumping water for some time, and that also went dry. So I had to go for the third bore well. And now the third bore well, the first bore well, maybe he had saved some money, and so he used that money to put the first bore well. Second bore well, maybe somehow he adjusted and begged and borrowed and got some loans and went for the third bore well. Second bore well, which also went dry, and he had to go for the third bore well because he was dependent on the water from the groundwater. He was dependent on the groundwater. So now what has happened with this chap is that he has he had to keep his land with the money lenders, okay, as a security. And then he has taken the money and then went for the third bore well. And now imagine what can happen to him if the third bore well also fails. He'll lose the land. This is more or less the situation, not just the place where I used to do my studies, particularly during my PhD, but it is also the case in most of the places around, okay, particularly where the system is overexploited. Okay, so let's go ahead now. I hope you are getting a feel for it, but if not, I'm always there to help you out even after the presentation. Keep that in mind, okay, please. So let's go ahead. And what do we have? Now let's go to the next aspect of sustainability, principle of sustainable development. There, it is about, it has to do with hydrology, with ecology, and geomorphology and climatology. Okay, when you're talking about groundwater sustainability, you had to address all these aspects. Okay, it's not just to model and do a few things and then you can talk about sustainability. No. Right? So finally, how much of water you have to recharge and how much of water that you can pull up and from where you will pull up during what part of the year that you'll pump out the water is all dictated by many other things like the ecology and then social aspects of the area and the economic aspects of the area and so on. Okay, so this was put up here. This was put up here. This is put up to bring to your awareness that sustainability is not a simple thing. Okay, it is a very involved thing. Fine. So let's go ahead now and. Right, and so you see that it is a function of depletion of the groundwater storage, reduction in stream flow. I just explained to you how the stream flows get reduced. Okay, maybe I'll explain it once more a little later. And then you have potential loss of wetlands and riparian ecosystems, and then changes in groundwater quality and a few other things. Okay, now question arises: you have the system, Okay, so you have the system, and then this is the groundwater levels in the system. So you have recharge. And there is a little of what you call inflow from the deep aquifer, and then you have this base flow. Okay, this base flow is going to the stream. Okay, so for example, if this is the topography, this is the topography, and so this is your groundwater table. This is your groundwater table. Fine, groundwater table, and this is the stream. Fine, this is the stream. And so your what is going to the stream here? This is your base flow. This is your base flow that you're talking about. So what you see here, what you have written here is nothing but this. Okay. Right. Now you have a recharge going into the system, right? And let's neglect this part. Okay. So you have a base flow. Now, how much of water can you pump out? How much of water you can pump out? There should be some way of knowing this, right? So how much of this is what we call a safe field, okay? Safe field. Now, for people who are not what you call deep into all this, you can directly say that RE can be equal to your pumping. What will happen when your recharge is, the whole of the recharge is pumped out? The base flow vanishes. The base flow vanishes, okay? Right? And then if your pumping is more than recharge, the system keeps on emptying. The groundwater levels keeps on dropping, okay? And finally, it reaches the base of the aquifer. Now, what decides how much should be the safe field is what we'll look into. And let's see what all I have brought for you, okay? All groundwater flow must be discharging somewhere, and abstraction will reduce these discharges. We are talking about base flow here, okay? So this discharge, discharging, this is what we call as base flow. Fine, this is the base flow. Done. Let's go to the next one now. And now, right? So what happens when, let's go read it here. Discharge to the streams and the lakes required to sustain discharge to the streams. How much of discharge should you maintain? And that is that much of discharge to streams and lakes required to sustain downstream water supply or the river ecosystem. Okay, that much of discharge has to be maintained, or that much of base flow has to be maintained. Okay, so you see this figure here, and you see this is the groundwater table. This is the groundwater table, and then the trees, the roots of the trees are in contact, and they pull up the water. And what we call as evapotranspiration. Technically, we call it as evapotranspiration. And you see here the plants are dependent on the groundwater table, okay, on the groundwater table. So this is what we mean by maintaining adequate base flows or discharges from the ecosystem point of view. Okay, let's go to the next point now. Here we have maintain groundwater table at depth such that water is accessible to the roots of the plants and the trees, and then discharge via freshwater wetlands and brackish lagoons through natural vegetation. Okay. Now, I know in hard rock aquifers we usually don't, and at least in Karnataka we very rarely come across wetlands. Maybe in forested areas you do have some wetlands, okay. But then wetlands have their own ecosystem. It's not that you can say you will not have wetlands, okay, right? If you want to protect your natural systems, wetlands are part of the systems, and wetlands are those places where the groundwater table has come up to the groundwater level, to the ground level, okay, to the ground level, fine. And so let's go ahead now. And so discharge to ocean to control saltwater intrusion problem. You have saltwater intrusion when we are pumping more water than the recharge, okay. So this maybe it requires a complete what you call presentation to teach you what you call tell you about saltwater intrusion problem. Now is not the time, but then just be aware that more of pumping can also lead to saltwater intrusion problems, okay. And so let's go ahead now, and now let's talk about where do we stand as far as the country is concerned, okay. Look at it now. Now, I'm talking from India point of view, okay. All this information is available, okay, and available in what do you call references that I'll bring to notice a little later. So read this now. You have 92% of 92% of the groundwater is utilized for irrigation. Are you aware of this? Are we aware? Forget about you, okay. Are we aware of such things? The general tendency is to believe that all the irrigation is done through surface water sources, like you build a dam, store water in the reservoir, and from the reservoir you take the water through the canals. And so the general belief is that all the irrigation through the country is done through canal systems, through canals, and also rain-fed, okay, which is not the truth. Look at this now. 92% of the groundwater is utilized for irrigation. So you do a lot of irrigation from the groundwater system, okay. 8% of the domestic and industrial users come from groundwater, okay. Now, there are 22 million wells which are operational in the country. And look at it, 85% of the rural water supply comes from the groundwater sources, okay. Very, very important to make a note of, right? Particularly the villages which are very deep in the countryside, they are dependent, highly dependent on, most of the villages are dependent on groundwater for their survival. It says 85% of the rural water supply comes from groundwater sources, okay, right? Now, more than 50% of the urban and industrial water supply comes from groundwater systems. At least two-thirds of irrigated area food grains production comes from groundwater irrigated lands. You're talking about two-thirds of our food coming from where? Which is being irrigated by groundwater systems, okay. Rather, groundwater is what is irrigating, and then from that we are getting two-thirds of our food grains. 80% of additional irrigated areas in the last 2 decades have come due to groundwater, because there were groundwater resources, because of groundwater pumping. 80% of additional irrigated land has come up due to this, okay, because there was groundwater. Now, maybe it's very difficult to comprehend all this in a very short period of just 1 or 2 minutes, but just to tell you that we're deep into it. We are deeply connected with our groundwater resources, and contrary to the belief is that all the irrigation is done through surface water systems. It is not so. The groundwater system plays a very, very important role, and particularly from things like this, which you're aware of. 85% of the rural water supply comes from groundwater sources. Okay. Now, let's go. And then I just wanted to bring this to your notice. Look, you have canals here. I'm using red to show you canals. Okay, this is this graph starts from 1950s and goes up to 2000, around 2000. Okay, the surface water systems, they are not developing, but whereas the groundwater system, the bore wells, and there is a continuous growth in the bore wells and then groundwater irrigated systems here. So you see that on this side you have area irrigated, and and more and more of irrigated area is being added due to the borewells. Hence, the borewells are continuously increasing. Okay, right? Now, this is something that you have to make a note of. Contrast between the groundwater system and the surface water system. Done. And let's go to the next one now. You have, look at this now. 60% of the irrigated agriculture is done through groundwater. 85% of the drinking water supplies comes from groundwater. Okay. Now, urban residents increasingly rely on groundwater due to unreliable and inadequate municipal water supplies. Okay. A-grade towns and B-grade towns, they are much dependent on groundwater systems. Okay. Even in a city like Mysore, much of the city is dependent on groundwater supplies, or they pump out water, groundwater. And a large part of Mysore city is dependent on groundwater and the bore wells. Okay. And now there are other aspects that are important. Maybe due to lack of time, I would like to skip them. Okay. Now, let's go ahead with a little more of information. In India, groundwater level has declined. What has happened to the system now? Let's look at that was the dependency, and now we are looking at what has happened to the system. 61% of the groundwater level have declined. Okay, by how much? 61% has been the decline. Okay, right, between over 10 years. This is 10 years here. This is 10 years. Over 10 years, 61% decline in the groundwater level. What do you mean by that? So this is the level earlier. Okay, and now this is the present level, and then you take the difference. This is over the decade now. This is over the decade, right? And compared to the other earlier years, there has been a drop of 60% roughly. That's the idea. Okay. Well, more important is this one. This term here. There is a decline in groundwater levels. This is what you see here. Okay. This is I have been handling with a lot of bore well data, and in almost all the bore wells, you see a decline like this. Okay, and then due to this declining levels, you see that people have been deepening their wells. Okay, and this comes at high cost, right? High cost of digging up a well, installing a bore well, and also high cost of pumping the water using the electricity. Okay, right? So the maintenance costs and electricity costs are high now. Done. And now investments are also increasing because when the water levels drop, you have to go for deeper wells. Okay. These are the consequences. This is where the country stands now. And now from the point of view of your farmers, they have very deep wells now because the water levels have dropped, and hence they had to go for more hardy crops. And now, but still they would like to go for cash crops, and there are failures of wells. And now then due to the depths that I was talking to you about, you have your suicides and then huge problems as far as the farmers are concerned. Okay, right? Now let's come to Karnataka now. And what do you find in Karnataka, right? Now, you may not be able to comprehend this. It's difficult to comprehend these figures, but then what is important is we have 75% is a stage of development. Okay, so we call it as development stage of development is 70%. What do you mean by 70%? Is that on an average, we have some recharge, okay? So how much of water is being used? 0.7 times of this recharge is being used on an average for the whole of the state, okay? This is what we mean by stage of development. So whatever recharge that you have estimated for the state of Karnataka, you are at a level where you are using 70% of the recharge water. This is not this is the average figure, but in reality, it is different. Okay, some places are more stressed and some places are less stressed. We'll come to that after this. Okay, so let's go ahead now and let's read this. Over 60% of the irrigation, and we are here. Okay, we are here. 60% of the irrigation and about 85% of the rural drinking water is due to groundwater, from groundwater. Okay, this is the dependency. I don't think many of us ever knew about these things. Okay, I'm trying to bring to your notice how important groundwater resources are and how important maintaining the sustainability of these groundwater resources is nowadays. It's high time we started looking into it. Okay, right now, let's go ahead now. This just to give you an idea. Look at it now. There is something known as recharge assessment, and I think everyone knows what a taluk is, and the recharge assessment was done in 175 taluks, and in this 175 taluks, almost about 50% are overexploited. You are withdrawing more water than recharge is roughly what we mean by overexploitation. Okay, critical is almost, if your pumping of water is almost equal to recharge, you have a critical situation, and there are 8 of them. Semi-critical is little lower than that. If your withdrawal is much less than your recharge, the area is known as semi-critical. Okay, and safe is your pumping is much less than your recharge, then you call it as safe. And there is a way of doing it. How to do this? I'll explain this to you very soon. Okay, right? And in Karnataka also, you see this, right? This graph, it is there for about maybe 20-30 years, and you see that the blue is for tube wells, and this is the extent to which the area is being irrigated. The scale on the y-axis is the hectares of land that you're irrigating through groundwater. And please study this graph now. The violet color is, here it is, okay? The violet color is, this is the violet color that you're talking about. This is the violet color, right? And canal irrigation, surface water irrigation is almost stagnant now, right? But whereas your groundwater irrigation, what I'm just drawing now, see here, the blue one is due to groundwater irrigation, due to through the tube wells or bore wells. Look at it now, this is what you have. And it is continuously rising. It has not even stabilized, okay? There is still a rise in it. Done? So this is the status of groundwater system in Karnataka, okay? Let's go ahead. And that's what you see, the bore wells increasing. And now you have an extra bit of information which is also critical. Bore well growth rate of 10.7% per annum from 1990 to 2016. Okay, what does it mean? Every year, let's say 1990, the bore wells were 100. Okay, so 1991, the bore wells were 110. And 1992, the bore wells were again 1.1 of 110, and that's how it's increasing. Okay, it's an exponential increase, and that's what you also see in this figure here. It's an exponential increase that you see here in this figure. Okay, done. So let's go ahead. This is the status of groundwater system in Karnataka, and I have a little more of information for you to sensitize you how where we stand in Karnataka as far as groundwater resources are concerned. Exploitation of groundwater has led to, look at this now, more than 3 lakhs of dug wells have dried up. Okay, half of the state's cultivated area has come under critical areas or overexploited areas. And now all the shallow bore wells have dried up. They have failed. Okay, and from the bore wells, the discharge is increasing because the bore wells are deeper and deeper. And then along with it, you don't cut many fractures as you go deeper and deeper, and so your yield is decreasing, okay, right? And so the irrigation capability is lower now. It has decreased from 7.8 hectares to 1.5 hectares per borewell. This is how much you can irrigate, okay, effectively. Now, along with it, quality of water, groundwater is also decreasing. These are the problems that we are facing in Karnataka, okay, right? Karnataka is one place where, which is highly dependent on groundwater pumping. Rather, the irrigation is dependent on groundwater resources. Okay, now, um, much of our problems is caused due to the free electricity that is supplied to the irrigation pump sets, okay? Right now, this I'm not what you call presenting this. I did a careful job. I have a lot of references what you call supporting this. Right now, up to about 7.5 HP, if I'm right, okay, the electricity that you use is free. And now in the state of Karnataka, you know, they give 7 hours of electricity over a day. Over a day, 7 hours of electricity, maximum 7 hours of electricity is provided to you. And if you wear your pump, you know, the borewell pump, if it is less than 7.5 HP, there'll be no charges for you. And what's happening now? Continuously, you invest in a borewell that comes to about, I think, around lakh rupees, 1.5 lakh rupees, and then electricity is free. You're continuously pumping out the water in a place where you could hardly go for very hardy crops like jowar and maize. You are growing rice now. And at what expense? You're withdrawing more water than was being recharged. You're pumping more water than what was being recharged naturally. Okay, now what happens due to this? The water table starts dropping. Not just in the farmer's land, but also it happens in overall the whole of the village. And just not in one village, in more or less 5-6 villages around, you know, the water table is falling. And what's happening to the farmers now? They had gone for the first bore well, and they had to go for a second deeper well, and then even that was not good enough to provide a good yield, and so they had to go for a much deeper well and more wider well, and they're in trouble now. Okay, the whole of the community that is dependent on groundwater is in trouble now. Okay, and much of it is because you have provided free electricity. Okay, now it's not to get into any controversy. This is a little debatable. In an economy like ours, should farmers be provided free electricity? Maybe from other points of view, yeah, correct. But from groundwater point of view, it's a big question. Okay, should you be providing free electricity from groundwater resources point of view, from the sustainability of groundwater resources? Should it be done or not is a big question. Okay, so this I explicitly mentioned here. It's not to get into any controversy. This is a topic that can be debated on. Okay, right? And these are potential areas where people like you can work. This is the places where work is required. Okay. Research work is required. Your PhDs have to be done in areas like this. So let's go to the next part now. So this is, and again, these are some of the, you have something known as groundwater yearbook for, and these yearbooks are for most of the states. And I'm taking from the Karnataka groundwater yearbook for 2016 and 17. And what you see here is this, okay. This map, you know, this is for a decade. Okay, you see that it is from 2006 to 2016. This is 10 years. Okay, over 10 years, what you see is that there is a fall here, almost 4 meters of fall. Rather 2 to 4. Let's say 2 to 4 meters of fall is there. The red here, you know, the lighter red. And the lighter red says that there is a groundwater fall of 2 to 4 meters everywhere. And there is a big repercussion due to this. What happens when the groundwater level falls by this much? Your open wells go dry. All the open wells go dry, and then affects hugely the tanks, the ponds and the lakes. They are affected very hugely. This looks to be trivial. 2 to 4 meters looks to be trivial, but has a very big consequence, has a big repercussion as far as your hydrology is concerned. Your wells, your open wells go dry. And then your tanks, the groundwater levels are much below your tank bed. And what happens now? During non-rainy days, the tanks are feeding to the groundwater system. The tanks get emptied very fast. This is the state of affairs in the state of Karnataka. Okay, and these are the figures from the government manuals and sources. Okay, so let's go ahead now. I think we are running short of time now. This is again explaining to you. I explained this many times earlier. This is what you see at the top here is the groundwater balance. Okay, so this is the groundwater balance, right? Recharge minus R stands for recharge, Q stands for pumping, and D stands for the base flow, and that is equal to your storage change. Okay, right? This is in natural conditions. As you see here, this is for natural conditions. And this is for when you have started pumping, okay? Like you see that with S, there is a small minus. Minus means the storage is decreasing. And because the storage is decreasing, the base flow is also decreasing. So D also has a minus sign there. Let's see what happens in the next figure. You have more of pumping. Q stands for pumping. So storage further decreases, and also the base flow decreases. The base flow to the nearest stream also decreases. Okay, so this is what is happening due to pumping. Again, I'm reiterating, okay, through different graphs and different explanation, I'm reiterating what happens when you go for over pumping, over exploitation. Okay, now when can an aquifer be said to be overexploited? An aquifer can be said to be overexploited when its groundwater levels show evidence of continuous long-term decline. The long-term average rate of groundwater recharge is less than abstraction. Okay, recharge is less than abstraction. Right, that's when we call it to be overexploited. Keep that in mind. Overall cost of negative impacts of groundwater exploitation exceed the net benefits of groundwater use. Okay, right? So cost andre, it is not just money point of view, it is from economic point of view, social point of view, and all these costs get what do you call connected. Okay, it's not just in money that you have to think about the problem. You have to also think about the problem in other aspects like social aspects and cultural aspects and other things. Okay, right? Now here is something that is of interesting. The aquifer overexploitation is an emotive expression not capable of rigorous scientific definition. So this is something that you can debate on. Okay, so let's go to the next slide now. When can an aquifer is said to be overexploited? Illy, I'll just take 2-3 minutes to explain this part now. Stage of water extraction. Read this now. Stage of water extraction. Here, existing gross groundwater extraction. Andre idu pumping. Pumping in the numerator you have pumping. In the denominator you have recharge. Okay, right? And that tells you the stage of groundwater extraction, right? And now you have. I'll once more want to stress it. In the numerator you have pumping. In the denominator roughly you have the recharge. Okay, so now look at this now. Stage of groundwater extraction, if it is less than 70%, you call it as safe. And when it is 70 to 90%, you call it as semi-critical. And between 90 to 100%, you call it as critical. And when your extraction is more than 100%, you call it as overexploited. And now here in this graph, this is for the country. I took only South India because of lack of space here. And much of this, it is in Karnataka. This is where Karnataka is. You see a lot of red there. Just to say that much of Karnataka is overexploited. You are withdrawing more water than recharge. This says that it's high time that we got into sustainable management of groundwater resources. Okay, fine. And then this is the resources. Anyway, I'll share the resources with you separately. It's very interesting to be reading all this. Okay, and now when it comes to Karnataka, now you know what is overexploitation, what is critical areas which are under critical conditions. You see that 17% of the area in Karnataka is overexploited from groundwater point of view. And about 20% of the area is in critical condition. So we are not in a good condition at all in Karnataka. It's high time we brought in a good management of our groundwater resources. Okay, so maybe I'll skip this. This shows for the whole of the country. Okay, now this is for South India. He shows for different parts of India. This is for South India, and we see this figure here. Roughly 22% is overexploited. 22% of South India is overexploited, and then about 7% is in critical condition. We are talking about South India here, okay, right? Now, now this I have been talking only about quantity of water till now. We never did talk about quality. Sustainability also is involved with quality of groundwater resources, okay? If the groundwater quality drops, just to say that you are what you call playing with the sustainability of the groundwater system, okay, right? So I told you why I did not pay attention to the quality aspects here. As it is, we are grappling with flow modeling. Okay, very few people have been working with quality modeling because the data is not available. As it is, the data is not available for you doing groundwater modeling, for flow modeling. Forget about getting good data sets for quality modeling. And you are required to collect your own data, okay, for flow modeling. And it's not a joke, okay, it's very expensive, very time consuming. And so that's the reason why I gave less of impetus. That's not to say that it is not important. It's very, very important that you also make your groundwater system sustainable from quality point of view, okay? So vulnerability is what we call, if the groundwater quality is being affected, the system is becoming vulnerable, okay? That is what technically they have been calling it. And when does the system become vulnerable, the groundwater system vulnerable from quality point of view? When the table is shallow and so on, okay, right? And you also have tools to what you call find out if the groundwater system is vulnerable to pollution, so that you can give more of impetus and attention to such areas. And you have these tools, okay? One is GOD and the other one is drastic. They are mnemonics. For example, GOD stands for groundwater occurrence, overall lithology, aquifer, and depth of water. These are index models. Okay, these are index models. You can work these models on GIS. You can work these models on GIS. Okay, I'll show you. You'll get an idea about this. The next slide that I present to you. This is where it is. Okay, so you have built layer upon layer. Each layer stands for example, here depth of the water, the recharge, and then the type of aquifer, the type of soil, and the slope and the topography, and so on. So each layer is built and it is given certain scores. So finally, it adds up to a certain score on which you build a index map like this. Okay. Now, if you were to look at this, you see that green, it is low vulnerability. And when you have yellow, moderate vulnerability, and red stands for very high vulnerability. So final score, you convert into index, and then that index is used on the map to know where there is high vulnerability. This is roughly about how you can also bring in vulnerability into your sustainability of groundwater resources. Okay, fine. Coming to the next one now. Look, now we have understood what do you mean by groundwater system. It's modeling, and then what happens when we pump, and what happens when we over pump, and then how do we, counteract this? We counteract it by artificial recharge, and all this, you cannot manage it at a farmer's level or an individual level. Right? You had to go for a structured approach for this, and what that structured approach is integrated watershed management. Okay, so your sustainable groundwater development should be a part of what now? Integrated watershed management. So your groundwater development should be a part of watershed management. Okay, right? So why should it be? Because there is a close interaction between your surface water and the groundwater. It's foolishness to talk only about groundwater without giving attention to surface water. If that's the case, you have to go for integrated watershed management. Okay, 1 second, please. I'm sorry. Artha aita. So without integrated watershed management, you have less of a meaning for sustainable groundwater development. That's what I wanted to bring to notice, right? So you had to make a study of integrated water resource management or integrated watershed management. And what do you mean by that? Give me 1 second to read it. Coordinated development and management of surface water and groundwater, land and related resources. Management of all this, would be called as water resource management. In order to maximize the resultant economic and social welfare in an equitable manner, without compromising the future, okay, right? And things like this, okay. So you have a what do you call a recharge tank here, and which has to be done at a community level, You see that here. You have another recharge tank here. Individuals cannot be doing it. Even a village cannot be doing it. You require a framework and a support, government support, private sector support to do all this. This is what you call as integrated water shed management or water resource management, okay, right? And and then look at this now. In integrated water shed management, these are the agencies, that are involved. You have government agencies, and then government institutions, government agencies, local authorities like your panchayat, and then your private sectors, and then civil society organizations, and then you have partnerships, and then maybe involvement of the World Bank, and then Asian Development Bank, that is the financing people, and so on, okay, right? And so these people, all these people are involved with your watershed development. And then incidentally in Karnataka, we have a watershed development department, and which has watershed development schemes, and roughly they have allocated about 400 crores for this, okay, where they're developing 2,500 micro watersheds, right? And obviously part of this watershed development process is your groundwater resource development, okay? So I think we are losing time now. We have very less of time. Let me hurry a little. So what I'm trying to bring to your notice is technically understanding is not sufficient enough. If you want to implement it, you cannot do it at an individual level or a small organization level. You have a lot of people, a lot of organizations and others involved with it, and then has to be implemented. The sustainability of groundwater resources has to be looked in the framework of integrated watershed management. That is what I wanted to bring to notice. I hope I have done a small good job of this now, okay? Right? Now, emphasis on, maybe we can skip this, okay? Let me skip this. Now, what is important is, look, what did we bring in here? We said that in this slide, we said that this many people are involved, okay? We also had the important stakeholder here, the farmers that are involved, okay? We did not talk about them, or rather the communities that are involved on this side, okay? Right? So you have all these organizations and these communities involved. Please bear with me for a few more minutes. I'm almost to the end of my presentation now. So we have all this institutions and then organizations involved, and also we have your farmers and then your villages and communities involved, okay? Communities involved. Now, there should be some rules by which all these people should be operating, okay? So we are talking about rules now, right? And rules and regulations. If not, there'll be chaos. There'll be chaos. How do you operate unless you have certain rules to guide you? And that's where this next slide comes into. And let me go a little formal now. What do I have here? Regulation of overexploitation of groundwater through legal means, okay? Right? So you want to regulate your overexploitation, that has to be regulated, can be regulated only through legal means. If not, who's going to hear you? They are more worried about their family economy. Any farmer is more worried about his profits. And he will not be worried. He is short-sighted, and he is not worried about the depleting groundwater levels. It's only the bigger organizations, the state, who recognizes this fact of depletion of groundwater systems, and so they bring in the rules, and then they control the farmers, the village communities. Okay, so in this, as far as your authorities are concerned, the authorities who control the groundwater resource in the country, you have the Central Groundwater Authority, okay, and And as far as the states are concerned, it's important. Okay, water is a state subject. You see that here. Water is a state subject. So what the Central Groundwater Authority has done is that they have given the bills. Okay, see it's here. Okay, they circulated the bills, and what we have done is we have our uh, groundwater. This is it. Groundwater Act in Karnataka. Most of the states have their own groundwater act now. Okay, right? So let me go back. Let me bring the focus to you now. So as far as the country is concerned, we have the Central Groundwater Authority. Their major work is to identify where the groundwater systems are suffering in the country, and also they have circulated the model bills. Based on these model bills, almost all the states have gone for their own state groundwater bills. Okay, and now in especially in Karnataka, we have what we call a groundwater directorate. Okay, to manage the groundwater system, and their job is to what do you call do the surveys and then carry out some projects and so on. Okay, hydrogeological projects. And now, when it comes to the bill, we call it as Karnataka Groundwater Act 2011, rules and regulation. Okay, rules and regulation, and due to this, there was the establishment of groundwater authority, right? And so under this groundwater authority, we have district groundwater committees. Okay, what is their job? The job is here. They have a power to notify areas which are overexploited or which are critical. They can notify these areas, and then they can start regulating it. Okay, now how do they regulate it? So look here, grant of permit to extract water. They start controlling the extraction water. On what basis? You had to control extraction of water on this basis. Okay, I listed this out now. If anyone's interested, you can download this directly from the web, or you can send me an email. I can send you this act. Okay, it's in PDF form, right? For example, use of groundwater in the notified area is based. The grant of permit to extract groundwater is based on these factors. Okay, for example, if they notice that there is a long-term groundwater level drop, they may notify that area as a notified area, and then they can stipulate how much of water can be withdrawn and so on, so on. Okay, so this is taken care of by district groundwater committee. The deputy commissioner is, I think, incidentally, the person who heads this committee in every district. Okay. Now, this was about regulation. This was about regulation. So if you want to make your groundwater systems sustainable, you had to be working with a lot of organizations and under the rules and regulation, and then you can think about making your systems sustainable. It becomes feasible, practical then. Okay, right? Now, the last thing, I require 2-3 minutes for this, and what I wanted to bring to notice is the tanks, the existence of tanks, particularly in South India. I'm talking about South India, okay, Tamil Nadu, and then Karnataka particularly, where you had every village had a pond, and technically I'm sorry, technically in our places we call this tanks or ponds as tanks. Okay, ponds are nothing but tanks. Okay, right? So every village used to have a tank, a small tank, maybe as big as about 2 acres here. Okay. Now there were huge tanks also at a bigger scale, and maybe where water could have been gathering from 4 or 5 catchments, and as big as it's a very popular tank on the way from Mysore to Bangalore. From Bangalore to Mysore, there is a place very near Srirangapatna. This is known as Tonnur Kere. Kere stands for pond. In Kannada, Kere means pond. Okay, so it's about 2,200 acres of a pond. Made about 150, 200 years back. Okay, this was constructed 200 years back around. Right now, if anyone's interested, you can refer to this what you call a book called as Tank Irrigation. The title of the book is Tank Irrigation Karnataka Historical Survey. It tells you the importance of tanks. Okay, every village had a tank earlier. Now, what has happened now is okay. Now, what has happened? I'll just tell you a little later. What is the importance of the tank? So this is what happens now. You have tanks, sorry, you had lakes and streams, and this was the natural system. So the blue here, the blue line here, this is the blue line. That is the natural groundwater table. And you start pumping. And when you start pumping, the groundwater levels drop. So you see that orange now, the orange is here, okay? And now after you do more of pumping, your groundwater table is so deep now, you are going below your stream, or cutting the stream, and you're going below the lake now. So groundwater table is unconnected with the lake now. Okay, what happens due to this now? The earlier, here, I'm here. Earlier, what used to happen was from uphill, the groundwater used to come to the lake, fill up the lakes, and then from the filled lake, the groundwater used to move downstream again. This is your upstream part, and this is your downstream part. This used to happen earlier days when you had no pumping and the water table used to be very high, and the water table used to interact very closely with the ponds. So in monsoon times, the lakes used to fill up. Groundwater also used to flow to the ponds. During summer times, non-monsoon times, the lake water used to feed your groundwater table. And so downstream of this tank, this pond, you used to have open wells and used to find water in the open wells. So what I'm trying to bring to notice is that tanks had a very, very, very important role to play. And sadly, most of the villages, the tanks are dry. And they fill up only during monsoon times. Immediately after the monsoon, the tanks are dry. So you don't have a interaction between your tanks and the groundwater system. You don't have a interaction. The groundwater table is too very deep. Okay. Now, due to this, what has happened now? A decline in importance of, what are the issues connected with the tanks in Karnataka? Decline in the importance of tank irrigation. Why did it happen? You started relying on pumping, tube wells. You started relying on tube wells. You started disregarding your tanks. And what happened was the tanks were not maintained properly, and there was a decline in importance of tank irrigation. The state had around 40,000 irrigation tanks with a command area of about 6.84 lakh hectares in 1980s, before pumping, right? The tanks are degraded and actually irrigated area got reduced to 2.4 lakh hectares. Earlier it was 6.84 lakh, almost two-thirds has come down, It has come down to 1/3 now. 2/3 has been removed, which is less than 35% of the design command area. Earlier command area, though, it only if it remains, only 35% remains now, right? And there are estimates indicating that of the total tanks, around 31% of the tanks are defunct, 31% of the tanks are defunct, and 80% of these tanks are medium and small scale, Now, maybe some of this figures it could be a little difficult for us to comprehend, but what I wanted to tell you was that there is a close interaction between the existence of tanks and the groundwater system, at least in Karnataka. So if I were to not mention this, I'll be doing a little of a disservice. So I wanted to sensitize you to this aspect also. I think I have covered most of the important aspects connected with the sustainability of groundwater resources. I think my 1.5 hours is also over. I hope it was not boring. We have come to the end of my presentation now. Thank you for your patient hearing.